And now in this lecture we'll answer two questions. In the first question, we find out the area of this big rectangle EFQH, and in the second question, we find out the area of this circle using two different methods. Repeat again. In the second question, we find out the area of this circle using two different methods. So we start with the first question. In the drawing, we have rectangle EFQH. Inside this big rectangle, we have three circles. The radius of this small circle equals to 5 units in its length. The radius of this medium circle is equal to 6 units. The radius of this big circle equals to 8 units in its length. Again, our task is to find out the area of this big rectangle EFQH. So first of all, we know that all the angles inside the rectangle are right angles. So those four angles are all right angles. So this is a right angle. This is also a right angle. This is a right angle, and this is also a right angle. In the next step, I'll present to you rule 1 and we'll implement rule 1 in our drawing. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Now, in the drawing, we have a circle. This is tangent AB, that is tangent to this circle at point M. And we have the radius OM, that is equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to this rule, rule 1. So we can implement rule 1 in our drawing. In our drawing, we have the medium circle. This is the medium circle. The radius QB of this medium circle equals to 6 units in its length. The radius QB is drawn to point B, that is the point of tendency of tangent HQ with this medium circle. And whenever your radius is drawn to the point of tendency, then tangent AQ will be perpendicular to the radius BQ. If AQ is perpendicular to BQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, this angle also equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. This angle equals to 90 degrees, and this angle also equals to 90 degrees. In the next step, we define the point of tendency of tangent FQ with this big circle. This point is point T, and we will join points S and T together by a straight line. ST is of course the radius of this big circle, that is equals to 8 units in its length. According to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. We define the point of tendency of tangent HQ with this big circle. This point is point L, and we join points S and together by a straight line. S is the center of this circle. So SL SL is of course the radius of this big circle, that is equals to 8. According to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in this quadrilateral STQL we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees. 270 degrees plus the size of this 4 missing angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4 missing angle must be equal to 90 degrees in its size. So inside quadrilateral STLQ, we have 4 rectangles, and according to rule 5, any quadrilateral that has 4 rectangles must be at least a rectangle if not a square. So relate to this small quadrilateral STQL as a rectangle because it has 4 rectangles. In the upper quadrilateral CFTS, we have 1, 2, 3 rectangles, and therefore this fourth angle must be equal to 90 degrees in its size. So inside quadrilateral SFTS, we have 4 rectangles, therefore can relate quadrilateral SFST is a rectangle. But you also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle CFST, side ST must be equal to the opposite side CF, but ST is 8. Therefore the opposite side CF must be also equal to 8 units in its length. The big angle CL, this is the big angle CSL. Angle CSL equals to 90 degrees plus 90 degrees is 180 degrees. And we know that any angle that equals to 180 degrees in its size, it is defined as a straight line. Therefore, CL is a straight line. CL is a straight line. And therefore, this shape CL, this shape ECL edge, this shape ECL edge has 4 sides, 1, 2, 3, 4. And therefore, this shape that has 4 sides is a quadrilateral. So in quadrilateral ECL edge, we have 1, 2, 3, 4 rectangles, and therefore quadrilateral ECL edge is a rectangle. So that you know, the big quadrilateral ECL edge is a rectangle because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So, in the big rectangle ECL edge, side, in the big rectangle ECL edge, side CL must be equal to the opposite side E edge. But CL in total is this 8 plus 8, that is 16. Therefore, the opposite side E edge must be also equal to, again, 8 plus 8 is 16. Therefore, the opposite side E edge must be also equal to 16 units in its length. E edge is the width of this big rectangle EFQ edge, and therefore we actually found out that the width for this big rectangle EFHQ is equal to 16 units. The only thing that is left to find is to find the length of this big rectangle. The length is EF, so we have to find out what is the value of EF, and the width times the length will be the area that we are looking for in this question, that is the area of this rectangle EFQ edge. In the next step, we will extend the radius BQ of this medium circle by straight line until it touches the rectangle at side EF, or until it touches side EF of this big rectangle EFQH. By doing this construction, we can do two quadrilaterals, two smaller quadrilaterals. So first of all, we define the touching point of the extended radius BQ with side EF. This point is point S. So by doing this construction, we get two smaller quadrilaterals. We have the small quadrilateral ESBH and this quadrilateral SCLB. This small quadrilateral SCLB, we have 1, 2, 3 right angles, and therefore this fourth missing angle must be equal to 90 degrees in its size. Likewise, in this quadrilateral ESBH, we have 1, 2, 3 right angles, and therefore this fourth missing angle must be equal to 90 degrees in its size. Therefore, quadrilateral ESBH is a rectangle because it has 4 right angles. So written on, quadrilateral ESBH is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in this rectangle ESBH, side ES must be equal to the opposite side SB. But EH is 16, therefore the opposite side SB must be also equal to 16 units in its length. So written down, SB equals to 16. In the next step, we will do another construction, that is to say, from point P, we will do perpendicular on SB. Again, from point P, we will do perpendicular on SB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point P and SB. This point is point X. By doing this construction, we're going to do the small quadrilateral ASXP. So the small quadrilateral ASXP, we have 1, 2, 3 right angles, and therefore this fourth missing angle must be also equal to 90 degrees in its size. So quadrilateral ASXP has 4 right angles, and therefore it is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So the small rectangle ASXP, side AP must be equal to the opposite side SX. But AP is 5, therefore SX must be also equal to 5 units in its length. QB equals to 6, SX equals to 5. So what is the length of this missing line segment SQ? XQ equals to SB minus SX minus QB. Repeat again, this is the missing line segment XQ. This is equals to SB minus X minus SX minus QB. So XQ in total equals to SB, SB is 16 minus SX, SX is 5, and QB minus QB, and QB is 6. 16 minus 5 is 11, and 11 minus 6 is 5. So if you found out that the missing line segment XQ equals to 5 units in its length. In the next step, we'll join point P and Q together by a straight line. Point P is the center of this small circle, point Q is the center of this medium circle. Therefore, PQ is the distance between the centers of the small circle and the medium circle. Those two circles have an external arc between them at this point. We define the attaching point. This point is point J, and whenever you have an external arc between two circles, you can implement rule 10. So repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects the centers together must pass through the attaching point. In the drawing, we have two circles. The center of this circle is at point O. The center of this circle is at point M. And the straight line that connects the centers together is, of course, the straight line OM. This is the attaching point. Point K is the attaching point. According to this rule 10, the straight line OM that connects the centers together must pass through point K, that is the attaching point. I repeat again, according to rule 10, the straight line OM must pass through point K, that is the attaching point, or OKM is one straight line. OKM is one straight line according to this rule 10. So can we implement rule 10 in our drawing? Well, because in our drawing, we have an external arc between the small circle and the medium circle at this point J. The distance between the center of those two circles is PQ. According to rule 10, the straight line PQ must pass through the attaching point, that is point J, or the straight line PQ must pass through point J, that is the attaching point, or PJQ is one straight line. Again, according to rule 10, PJQ is one straight line. If PJQ is one straight line, it means that PQ in total must be equal to PJ plus JQ. So PQ equals to PJ. PJ is the radius of this small circle, that is 5, plus QJ. QJ is the radius of this medium circle, that is 6. So in total PQ equals to 5 plus 6, that is 11. Why? Because PJQ is one straight line, therefore PQ must be equal to PJ, that is 5, plus JQ, that is 6, in total it is equals to 11. So this distance between the centers of those two circles is equal to 11 points, 11 units. In the next step, I'll copy the green right triangle PXQ. In the new page, we'll implement the Pythagoras theorem of this green right triangle PXQ. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse of this green triangle PXQ equals to 11 units in its length, and XQ equals to 5 units in its length. PX is the missing side. Here by PT is a ratio for Pythagoras theorem. So actually, this is the green right triangle PXQ that I copied from the original drawing. This right triangle PXQ, according to the Pythagoras theorem, PQ squared, that is the square of the hypotenuse, equals to PX squared plus XQ squared. So I write it down. PQ squared, that is the square of the hypotenuse, equals to px squared plus xq squared. PQ is 11, therefore PQ squared is 11 squared. That is 129, and it is equals to px squared. Px is the missing side, so we leave it as it is. So it is px squared plus xq squared. Xq is 5, therefore xq squared is 5 squared, that is 25. In total, we found out that 121 equals to px squared plus 25. Here we will subtract 25 from this equation, and we get that 121 minus 25 is 96, equals to px squared. Here we will substitute 96 by 16 times 6, and we get that 16 times 6 equals to px squared. Here we take root out of this equation, and we get that the missing side px equals to the square root of 16 is 4, so inside the root we left only with 6. In total, we found out that the length of the missing side px is equals to 4 times square root of 6 units. This is the missing side px, that is equal to 4 times square root of 6 units in its length. We already found out that the small quadrilateral ASXP is a rectangle, and you know that the opposite sides of a rectangle are equal to each other. So the small rectangle ASPX, side PX must be equal to the opposite side AS. But PX is 4 times square root of 6, therefore the opposite side AS must be also equal to 4 times square root of 6 units in its length. In the next step, we define the point of tendency of tangent EH with this small circle. This point is point Z, and we join points P and Z together by a straight line. PZ is of course the radius of this small circle, that equals to 5 units. According to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the small quadrilateral EAPZ, we have 1, 2, 3 angles. Therefore, this fourth missing angle must be equal to 90 degrees on its side, and therefore quadrilateral EAZP is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle EAZP, side ZP must be equal to the opposite side EA, but ZP is 5, therefore the opposite side EA must be also equal to 5 units in its length. In the next step, we join the center of this medium circle, that is point Q, with the center of this big circle, that is S. That is to say, we join points Q and S together by a straight line. SQ SQ is of course the distance between the centers of the big circle and this medium circle. The medium circle has an external between with this big circle at this point. We define the touching point, this point, as point Y. So here we can implement rule 10. According to rule 10, the straight line that connects the center of the big circle with the center of the medium circle is SQ, of course. The straight line SQ must pass from point Y, that is their tangent point. Again, the straight line SQ that connects the centers of those two circles together must pass from point Y, that is their tangent point. Or SYQ is one straight line. Again, SYQ is one straight line according to Rule 10. If SYQ is one straight line, it means that SQ must be equal to SY, that is 8, plus QY, that is 6. So total SQ must be equal to 8 plus 6, that is 14. Again, SQ must be equal to 8 plus 6, that is 14. In the next step, we do a construction. That is to say, from point Q, that is the center of this medium circle, we will do perpendicular on CL. Again, from point Q, we do perpendicular on CL. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point Q and CL. This point is point K. By doing this construction, you can do the small quadrilateral QKLB. Inside this small quadrilateral QKLB, we have 1, 2, 3 rectangles, and therefore this fourth rectangle must be also equal to 90 degrees in its size. And therefore, quadrilateral QKBL is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. The opposite sides of a rectangle are equal to each other. So in the small rectangle QKBL, side QB must be equal to the opposite side KL. But QB is 6, therefore the opposite side KL must be also equal to 6 units in its length. What is the length of this short line segment SK? SK equals to SL minus KL. So it is known SK equals to SL minus KL. So SK equals to SL is the radius of this big circle, that is equals to 8 units, minus KL. KL is 6. So total SK equals to 8 minus 6, that is 2. SK equals to 2 units in its length. In the next step, I'll copy the right triangle SKQ in a new page, and we will implement the Pythagoras theorem on this right triangle SKQ. The hypotenuse SQ equals to 14 units in its length, side SK equals to 2 units in its length, and QK is the missing side. Here by PT is abbreviation for Pythagoras theorem. So actually, this is the right green triangle QSK that are going from the original domain. In this right triangle QSK, SQ squared, that is the square of the hypotenuse, equals to SK squared plus KQ squared. Again, SQ squared, that is the square of the hypotenuse, equals to SK squared plus QK squared. So it is now SQ squared equals to SK squared plus QK squared. SQ, the opposite SQ equals to 14 units in itself, therefore SQ squared is 14 squared, it is 196, and it is equals to SK squared. SK is 2, therefore SK squared is 2 squared, that is 4, plus QK squared. QK is the missing sign, so it is it is. So in total we should find out that 196 equals to 4 plus QK squared. Here we subtract 4 from this equation and we get that 196 minus 4 is 192. So 192 equals to QK squared. We substitute 192 by 64 times 3. And we get that 64 times 3 equals to QK squared. Here we take a root out of this equation and finally we get that QK, limits inside QK, is equal to the square root of 64 is 8, so inside the root we left only with 3. So total we should find out that the miss inside QK equals to 8 times square root of 3 units in its length. So okay, this is the miss inside QK, that is equals to 8 times square root of 3 units in its length. We have already found out that we will focus on this quadrangle SCKQ. This is quadrangle SCKQ. This quadrangle SCKQ, we have 1, 2, 3 right angles, and therefore this fourth missing angle must be also equal to 90 degrees in its size. Therefore, quadrangle SCKQ is a rectangle because it has 4 right angles. So it is known quadrangle SCKQ is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle SCKQ, side QK must be equal to the opposite side SC. But we just now found out that QK equals to 8 times square root of 3. Therefore the opposite side SC must be also equal to 8 times square root of 3 units in its length. So if we found out that the length of this rectangle EFQH is EF, and EF in total equals to 5 plus 4 times square root of 6 plus 8 times square root of 3 plus 8. That is the length, and the width is EH, that is 16. And the length times the width is the area of this rectangle EFQH, that is the area that we are looking for in this question. So that is done, we found out that before that we have the equation that says that the area of any rectangle is equal to the width of the rectangle times the length. So the area of rectangle EFQH is equal to the width of the rectangle times the length. The width is the edge, again the width is the edge, and the length is the F. Again, the length of this big rectangle EFQH is the F. So the width EH times the length EF, it is the area of the big rectangle EFQH. EH, the width EH is 16, and the length EF is equal to EA plus AS plus SC plus CF. And therefore, in total, the area that we are looking for in this question, that is the area of rectangle EFQH, will be equal to the width, that is 16, times the length, that is EA plus AS plus SC plus CF. So the area total equals to 16 times EA is 5, plus AS. AS is 4 times root of 6, plus SC. SC is 8 times root of 3, plus CF. CF is 8. So in total, if you found out that this rectangle EFQH is equal to the width, that is 16, times the length, that is 5, plus 4 times root of 6, plus 8 times root of 3, plus 8. Actually, the value of this expression in total is equal to 586.47 square units. And that is the answer to the question. We actually found out that the area that we are looking for this question, that is the area of the big rectangle EFQH, is equal to 586.47 square units in its size. So we finished with the first question. In the next step, I will present to you the second question, and we'll solve the second question by using two different methods. In the second question, our task is to find out the area of this circle. So in the drawing, we have a circle. This is called AB. This is equals to 8 units in its length. This is called PQ. This is equals to 6 units in its length. This is angle PMQ. That is a right angle. Again, our task is to find out the area of this circle. So we start with the first method. And I'll present to you rule 29, and we'll implement rule 29 in our drawing. According to rule 29, peripheral angles that subtend on the same arc are equal to each other in their sizes. In the drawing, we have a circle. This is peripheral angle BDC. Is equals to alpha degrees in its side, and it's subtend on arc BC. Likewise, we have another peripheral angle, this is peripheral angle BEC. The size of peripheral angle BEC is beta, and peripheral angle BEC subtend on the same arc BC. And because of the fact that those two peripheral angles subtend on the same arc BC, they must be equal to each other in their sizes. That is to say, alpha equals to beta. So according to this rule 29, if two or more peripheral angles subtend on the same arc, they must be equal to each other in their sizes. So we can implement rule 29 in our drawing. Why? Because in our drawing, we focus on this arc BQ. This is arc BQ, So actually the red curve BQ is arc BQ. So we have triangle BAQ that subtend on the red arc BQ. Likewise, we have another triangle BPQ that subtend on the same arc BQ. And because of the fact that those two triangles subtend on the same arc BQ, they must be equal to each other in their sizes according to Rule 29. So if we define the size of this triangle BAQ as alpha, then the size of this triangle BBQ must be also equal to alpha, because they both subtend on the same arc and therefore they are equal to each other according to Rule 29. In the next step, we focus on arc AP. So this is arc AP. So in the drawing we have triangle AQP that subtend on arc AP. Again, triangle AQP subtend on this arc AP. Likewise, we have another triangle, that is triangle PBA. This is triangle PBA that is also subtend on the same arc AP. And because of the fact that those both triangles subtend on the same arc AP, they must be equal to each other in their sizes. So if we define the size of this triangle AQP as beta, then the size of this triangle ABP must be also equal to beta according to Rule 29, because both of them subtend on the same arc AP. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. But this vertex angle equals to 90 degrees in size, and therefore the other vertex angle must be also equal to 90 degrees in its size. The sum of the angles in the right triangle A and B must be equal to 180 degrees. It is true in any triangle, and therefore it also must be true in the right triangle A and B. So which angles we have in the right triangle A and B? We have angle alpha plus angle beta plus the right angle. In total, they must be equal to 180 degrees. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. Here we subtract 90 degrees from this equation, and we get that alpha plus beta equals to 180 degrees minus 90 degrees is 90 degrees. So alpha plus beta equals to 90 degrees. Here we will multiply this equation by 2, and we get that 2 alpha plus 2 beta equals to 90 degrees times 2 is 180 degrees. So if we found out that 2 alpha plus 2 beta equals to 180 degrees. In the next step, I'll present to you Rule 13, and we'll implement Rule 13 in our drawing. But before that, we'll define the center of this big circle. This point is point O. But first of all, what is a central angle? A central angle is an angle in a circle that its vertex is at the center of the circle, and its two legs are the radii of the circle. So according to Rule 13, a central angle is twice as large as the peripheral angle subtended on the same chord or the same arc. So in the drawing we have a circle. This is peripheral angle ACB. Is equals to 30 degrees in its size, and subtend on arc AB. Likewise, we have central angle AOB that subtend on the same arc AB. And according to this rule 13, the size of the center angle AOB must be twice as big as the size of the peripheral angle ACB that subtend on the same arc AB. The size of peripheral angle ACB is theta, and therefore the size of center angle AOB must be equal to 2 theta, because it is also subtend on arc AB. So the size of the center angle is twice as large as the size of the peripheral angle that subtend on the same arc or the same chord. So can you calculate rule 13 in our drawing? First of all, I will draw center angle AOP. Repeat again, the vertex of a center angle is at the center of the circle, and its two legs are the radii of the circle. So actually, this is center angle AOP. Center angle AOP, of course, subtend on RKP. Again, center angle AOP subtend on RKP. But we also have peripheral angle AQP that is also subtend on RKP. And according to rule 13, the size of the center angle AOP is twice as big as the size of peripheral angle AQP that subtend on the same arc RKP. The size of peripheral angle AQP is beta, and therefore the size of the center angle AOP must be equal to 2 beta. It's twice as big as the size of the peripheral angle that subtend on the same arc RKP. Likewise, I will draw the center angle BOQ that subtend on arc BQ. And then again, that this is center angle BOQ that subtend on this arc BQ. But we have peripheral angle BAQ also subtend on the same arc BQ. And therefore the size of the peripheral angle BOQ must be twice as big as the size of peripheral angle BAQ that subtend on the same arc BQ. The size of peripheral angle BAQ is alpha, and therefore the size of center angle BOQ must be equal to 2 alpha, according to rule 13. In the next step, we define angle POQ, this angle SX, and angle AOB, this angle SY. We have the rule that says that the sum of the angles around any point is equal to 360 degrees. I repeat again, the sum of the angles around any point is equal to 360 degrees. So the sum of the angles around point O, that is the center of the circle, is equal to 360 degrees. So which angles we have around point O? Actually, we have in total 4 angles. 2 alpha plus 2 beta plus x plus y. In total, the sum of those 4 angles must be equal to 360 degrees according to the rules that I mentioned. Repeat again. 2 alpha plus 2 beta plus x plus y equals to 360 degrees. But we already found out that 2 alpha plus 2 beta equals to 180 degrees. Therefore, we can substitute 2 alpha plus 2 beta in this equation by 180 degrees. So 180 degrees plus x plus y equals to 360 degrees. Here we subtract 180 degrees from this equation, and we get that x plus y equals to 360 degrees minus 180 degrees is 180 degrees. In total, we can find out that x plus y equals to 180 degrees. In the next step, I present to you rule 30, and we will implement rule 30 in our drawing. According to rule 30, center angles that subtend unequal chords are equal to each other. In the drawing, we have a circle. This is center angle COD that subtend on chord CD. In addition, we have center angle EOB that subtend on chord AB. According to this rule, rule 30, if chord AB equals to chord CD, that is to say, those two center angles subtend on equal arcs, then alpha equals to beta. Then they are equal to each other in their sizes. So repeat again, according to rule 30, if two or more center angles subtend on equal arcs, they must be equal to or equal chords or equal arcs, it doesn't matter. They must be equal to each other in their sizes. Repeat again, if peripheral angles, two or more peripheral angles subtend on equal chords, they must be equal to each other in their sizes. In this case, chord AB equals to chord CD, that is to say, those center angles subtend on equal arcs, then they must be equal to each other in their sizes. That is to say, alpha equals to beta. So I can implement rule 30 in our drawing. First of all, I'll copy this circle to a new page, and I'll copy also the center angle AOB that is equals to y degrees in size, and chord AB that is equals to 8 units in its length. And then I'll do a construction, and then we'll implement rule 30 in our drawing. So I copied the original circle to this new page with center angle AOB that is equals to y degrees in size, center angle AOB subtend on chord AB that is equals to 8 degrees in its length. In the next step, we will do a construction, that is to say, for point V, I will draw a chord that is equals to 6 units in its length. So this is code BC, that is equals to 6 units in its length according to my construction. Repeat again, code BC equals to 6 units in its length according to my construction. In the next step, we join points O and C together by straight line. By joining points O and C, you can then do straight triangle BOC. This is straight triangle BOC. That subset on code BC that equals to 6 units in its length. Likewise, in the original drawing, we have straight triangle POQ. This is also equals to straight triangle POQ equals to x degrees in its size, and it is also subset of code PQ that is equals to 6 units in its length. So we have here two straight triangles that subset on equal chords. Again, we have two straight triangles that subset on equal chords. They both subset on chord that is length, its length is 6. Chord PQ equals to 6 units in its length, and chord BC also equals to 6 units in its length. And because of the fact that those two straight triangles subset on equal chords, they must be equal to each other in their sizes according to rule 30. Repeat again, because of the fact that those two straight triangles subset on equal chords, that equals to 6 units, both straight triangles, they must be equal to each other in their sizes according to rule 30. But the size of this straight triangle is x, therefore the size of this straight triangle, B or C, must be also equal to x according to rule 30. And again, according to rule 30, straight triangles that subset on equal chords are equal to each other. Those two straight triangles subset on equal chords is equals to 6 units in its length, and therefore they must be equal to each other in their sizes. But the size of this straight triangle POQ is x, therefore the size of this straight triangle COB must be also equal to x according to rule 30, because they are both subset on equal chords. Okay, so by doing this construction, you can then do angle AOC. This is angle AOC. The size of angle AOC is x plus y. Again, AOC equals to x plus y degrees in its size. But we have already found out that x plus y equals to 180 degrees. That is to say, angle AOC equals to 180 degrees in its size, and we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore, AC is a straight line. AC is a straight line. But AC is a straight line that touches the circle at 2 points, A and C. And therefore, AC is a chord AC is a chord that passes from point O, that is the center of the circle, and we know that any chord that passes from the center of the circle must be the diameter of the circle. Therefore, chord AC is the diameter of the circle. So the non-chord AC is the diameter of the circle. Because of the fact that chord AC passes from point O, that is the center of the circle, chord AC must be the diameter of the circle. So here we can implement rule 7. Repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing, we have a circle. This is peripheral angle ACB. The subset on chord AB, that is the diameter of the circle, and therefore according to this rule 7, peripheral angle ACB must be equal to 90 degrees in its size. So according to Rule 7, any perpendicular that subset on the diameter of the circle must be equal to 90 degrees in its size. We can definitely implement Rule 7 in our drawing. Why? Because in our drawing we have perpendicular ABC. This is perpendicular ABC that subtend on chord AC, that is the diameter of the circle, and therefore according to Rule 7, perpendicular ABC must be equal to 90 degrees in its size. So in the next step, we will implement the Pythagoras theorem on this right triangle, triangle ABC. So I complete the right triangle ABC in the new page, and we will implement on it the Pythagoras theorem. The hypotenuse AC is also the diameter of the circle. So if we define the radius of this circle as r, then the diameter must be equal to r. So actually, this is the right triangle ABC, the corresponding drawing. In this right triangle ABC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. So write it down. AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is 2r, therefore AC squared is 2r squared, that is 4r squared, and it is equals to AB squared. AB is 8, therefore AB squared is 8 squared, it is 64, plus BC squared. BC is 6, therefore BC squared is 36. 64 plus 36 is 100. The total of 4r squared equals to 100. Here we divide this equation by 4, and we get that r squared equals to 100 over 4 is 25. So r squared equals to 25. Here we take a root out of this equation, and we get that the radius r of the circle is equal to the square root of 25, that is 5. So if you found out that the radius r of this circle, the radius r of this circle is equal to 5 units in its length. Our task is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. Repeat again. The area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared, so the area of our circle must be equal to pi r squared. So it is pi times r squared. R is 5, therefore r squared is 5 squared, that is 25. So in total, if you found out that the area of this circle, it is equal to either 25 pi square units in size, or in terms of numbers, it is equal to 78.54 square units in size. Repeat again, if you found out that the area that we are looking for in this question, that is the area of this circle, equals to either 25 pi square units in size, or in terms of numbers, it is equal to 78.54 square units in size. So we finish with the first method. In the next step, I'll explain to you how to find out the area of this circle according to the second method. In the second method, we use the sum of the things that we already found out in the first method. We already found out in the first method that those two angles are both equal to alpha. And those two angles are both equal to 90 degrees. So in the drawing, we have the right triangle A and B. In the right triangle A and B, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in a triangle. Likewise, in the right triangle P and Q, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha, according to the rule that the sum of the angles in a triangle is equal to 180 degrees. It is very easy to see that those two right angles are similar to each other according to angle similarity rule. I will explain anyway why those two right angles are similar to each other. First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. Finally, both those two angles are equal to 90 degrees minus alpha and therefore they are equal to each other. So if you prove that all the figures of the right triangle A and B correspond equal to all the figures of this right triangle P and Q, and therefore those two right angles are similar to each other according to angle similarity rule. So I write it down. If you found out that the right big triangle A and B is similar, this is the sign of similar to the right triangle P and Q, according to angle similarity rule. And from the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB of the right triangle A and B over side PQ of the right triangle P and Q is equal to side AM of the right triangle A and B over side PM of the right triangle P and Q, and it is also equal to side BM of the right triangle BABM over side MQ of the right triangle PMQ. Again, from the fact that those two right angles are similar to each other, we derive that the following relationship exists between their sides. We will derive that side AB of the right triangle A and B over side PQ of the right triangle P and Q is equal to side AM of the right triangle A and B over side PM of the right triangle P and Q, and it is also equal to side BM of the right triangle A and B over side MQ of the right triangle P and Q. AB is 8. Over PQ is 6, and it is equal to AM over PM. So if you found out that 8 over 6 equals to AM over PM. Here we will divide both the numerator and the denominator of this number by 2, and get that 8 over 2 is 4, and 6 over 2 is 3. So 3/3 equals to AM over PM. Here we will multiply both the numerator and the denominator of this number by A. And we get that 4A over 3A equals to AM over PM. It is allowable to multiply anything by 1. A over A is 1, so by multiplying by 1, will not change the value of the expression. We multiply this side of the equation by 1, so we didn't change the value of the expression. What is the meaning of this equation? The meaning of this equation is that if AM equals to 4A, then PM must be equal to 3A. So, the knowledge we found out that if AM equals to 4A, then PM must be equal to 3A. Those two sides of the equation are equal to each other. AB over PQ is 4/3, so 4/3 equals to BM over MQ. So write it down. 4/3 equals to BM over MQ. Here we multiply this side of the equation, this number of the numerator and the denominator of this number by B, and we get that 4B over 3B equals to BM over MQ. So what is the meaning of this equation? The meaning of this equation is if BM equals to 4B, then MQ must be equal to 3B. And again, according to this equation means that if BM equals to 4B, then MQ must be equal to 3B. So if you found out that if BM equals to 4B, then MQ must be equal to 3B. PB is a chord in this circle. PB is a chord, it is absolutely a straight line. So if we focus on the right side of the straight line PB at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of PB at point M? We have this angle that is the right angle, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this angle must be equal to 90 degrees in its size. In the next step, we join points B and Q together by a straight line. By joining points B and Q, we create the right triangle MBQ. So I'll copy this right triangle MBQ in a new page and we will implement on it the Pythagoras theorem. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle MBQ, this is the curvature of the original drawing, and this right triangle MBQ according to the Pythagoras theorem, BQ square equals to MB square plus MQ square. So I write it down. BQ square, that is the square of the hypotenuse, is equal to MB square plus MQ square. BQ is the missing side, so we notice it is, so it is BQ square equals to MB square. MB is 4B, therefore MB squared is 4B squared, that is 16B squared, plus MQ squared. MQ is 3B, therefore MQ squared is 3B squared, that is 9B squared. 16B squared plus 9B squared is 25B squared. So total we found out that BQ square equals to 25B square. BQ square equals to 25B square. Here we take a root out of this equation and finally we get that BQ, this inside BQ is equals to the square root of 25, that is 5, times square root of B squared, that is B. So in total, we actually found out that BQ equals to 5B units in its length. So here, this is the missing side BQ, that is equals to 5B units in its length. In the next step, we'll calculate the area of this triangle ABQ using two different methods. I'll repeat again. We'll calculate the area of this triangle ABQ using two different methods. And then we create an equation that says that the area of triangle ABQ according to the first method must be equal to the area of triangle ABQ according to the second method. So in the first method, we calculate the area of triangle ABQ according to the formula that the area of a triangle equals to the base of the triangles times the height of the base over 2. We choose the base of triangle ABQ is AQ. So the area of triangle ABQ according to the first method will be equal to the base AQ times the height of the base, that is MB. Why MB is the height of the base? Because it creates 90 degrees with the base AQ. So it is the base AQ times the height MB over 2. So according to the first method, we found out that the area of this triangle ABQ is equal to the base AQ times the height MB over 2. Now we calculate the area of triangle ABQ according to the second method. So here we have triangle ABC that could be a triangle. The length of side AB is A units, side AC equals to B units in its length, side BC equals to C units in its length. This triangle ABC that could be any triangle. The area of this triangle ABC will be equal to A times B, that is the multiplication of two sides by each other, times sinus theta over 2. So it is times sinus the angle between the two sides over 2. And again, the area of this triangle according to the new formula equals to A times B times sinus theta over 2. We use the new formula in order to calculate the area of this triangle ABQ. So the area of this triangle ABQ will be equal to AB times BQ. That is the multiplication of two sides by each other, times sinus the angle between the two sides, AB and BQ. So it is sinus, the angle between the two sides is angle ABQ. So it is times sinus angle ABQ over 2. So if you found out that they have this angle ABQ according to the second method of calculation is equals to AB times BQ, the multiplication of two sides by each other, times sinus the angle between side AB and BQ. And the angle between side AB and BQ is angle ABQ divided by 2. This equation says that the area of triangle ABQ according to the first method must be equal to the area of triangle ABQ according to the second method. Here we have 2 on both sides of the equation, so 2 will get cancelled. We have to find out the value of sinus angle ABQ. In order to find out the value of sinus ABQ, we will implement the law of sines in our drawing. So what is the law of sines? First of all, the law of sines is true in any triangle. This is triangle ABC, that could be any triangle. The length of side AB is units, side AC equals to B units in itself, side BC equals to A units in itself. This is angle alpha, this is angle beta, and this is angle gamma. In this triangle ABC, that could be any triangle, according to the law of sines, the following equation is true. That A over sinus alpha equals to B over sinus beta equals to C over sinus gamma. And it is also equals to 2R. 2R is the diameter of the circle that blocks this triangle. Again, 2R is the diameter of the circle that blocks this triangle, triangle ABC. So, we implement the law of sines in our drawing. First of all, the law of sines is true in any triangle, therefore we can implement the law of sines in triangle ABQ. This circle blocks triangle ABQ, therefore 2R will be the radius of this circle that blocks triangle ABQ. According to the law of sines, the following equation will be true, that if we focus on triangle ABQ, the following equation will be true. AQ over sinus angle ABQ. Again, AQ over sinus angle ABQ equals to 2R. And 2R is the diameter of this circle that blocks triangle ABQ. And again, according to the law of sines, the following equation will be true. AQ over sinus angle ABQ equals to 2R. Again, AQ over sinus angle ABQ equals to 2R. So now, according to the law of sines, the following equation will be true. AQ or sinus angle ABQ equals to 2R. This equation is the implementation of the law of sines in our drawing. 2R is the diameter of this circle that blocks triangle ABQ. Here we will multiply this equation by sinus angle ABQ, and then we divide it simultaneously by 2R, and we get that sinus angle ABQ equals to AQ over 2R. Okay, again, we actually multiply this equation by sinus angle ABQ, and then we divide it by 2R, and we got that sinus angle ABQ equals to AQ over 2R. And because of the fact that sinus angle ABQ equals to AQ over 2R, we can substitute sinus angle ABQ in this equation by AQ over 2R. We'll do it now, and we get that AQ times MB equals to AB times BQ times sinus angle ABQ. We substitute sinus angle ABQ by AQ over 2R. So in total, we found out that AQ times MB equals to AB times BQ times AQ over 2R. So here we have AQ on both sides of this equation, so AQ will get cancelled. After cancelled AQ on this side of the equation, we left only with MB. So MB equals to AB times BQ over 2R. So MB equals to AB times BQ over 2R. Here we will multiply the equation by R and then we divide it by MB, and we get that R equals to AB times BQ over 2 times MB. But again, if you found out that R, the radius of this circle R is equal to AB times BQ over 2 times MB. So the radius R equals to AB. AB is 8, according to what is given in the question, times BQ. We already found out that BQ equals to 5B. Over 2 times MB. MB equals to 4B. So in total, we actually found out that R, the radius of the circle, equals to 8 times 5B over 2 times 4B. So we have B in the numerator and B in the denominator, so B will get cancelled. We have 8 in the numerator and 2 times 4, that is 8 in the denominator, so those two numbers also get cancelled. And we left only with 5. So if you found out that the radius of this circle R equals to 5 units in its length. Our task is to find out the area of this circle. So actually you know that the area of any circle equals to pi times the radius of the circle squared. Repeat again, the area of any circle equals to pi times the radius of the circle squared. And therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared. So the area of our circle must be equal to pi r squared. So it is pi times r squared. R is 5, therefore r squared is 5 squared, that is 25. So in both methods, you have found out that the area of this circle is equal to either 25 pi square units in size, or in terms of numbers, it is equal to 78.54 square units in its size. So if we finish with the second method, in the next step, or some of the lecture, we'll start with the first question, of course. In the first question, our task is to find out there of this big rectangle EFQH. So in the drawing we have the big rectangle EFQH. Inside this big rectangle we have 3 circles. The radius of this small circle equals to 5 units in its length. The radius of this medium circle equals to 6 units in its length. And the radius of this big circle equals to 8 units in its length. Again, our task is to find out the area of this big rectangle EFQH. So first of all, we know that all the angles inside any rectangle are right angles, so those 4 angles are all right angles. In the next step, I presented to rule 1 and implement rule 1 in our drawing. According to rule 1, a tangent to a circle is perpendicular to the radius 1 to its point of tendency. So, in the drawing we have a circle. This is tangent AB, this is tangent to this circle at point M. The radius OM that is equals to R, the radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to this rule 1. We implemented rule 1 a lot of times in our drawing. For example, I take one case and I explain it, and we implement rule 1 automatically in the other cases without any explanation. We'll take for example this medium circle. The radius of this medium circle QB equals to 6. The radius QB is drawn to point B, that is the point of tendency of tangent HQ with this medium circle. And whenever your radius is drawn to the point of tendency, then tangent HQ will be perpendicular to the radius QB. If HQ is perpendicular to QB, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. We have this angle equals to 90 degrees, and this angle equals to 90 degrees according to the same rule 1. Likewise, this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule 1. Then we extended the radius CS of this big circle by actually we join points S and L together by straight line. SL is the radius of this big circle that is equals to 8. So according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. And we join points S and T together by straight line. ST is also the radius of this big circle that is equals to 8. And according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. By doing those constructions, we're going to do quadrilateral STQL. Inside quadrilateral STQL, we have 1, 2, 3 angles, and therefore this fourth angle must be also equal to 90 degrees in its size. Likewise, in the upper quadrilateral CFTS, we have 1, 2, 3 angles, and therefore this fourth angle must be equal to 90 degrees in its size. So the big angle CSL equals to 180 degrees, and therefore CL is a straight line. If CL is a straight line, it means that shape CLHE has 4 sides, 1, 2, 3, 4, and therefore it is a quadrilateral. But in quadrilateral ECLH we have 4 angles, 1, 2, 3, 4. And therefore quadrilateral ECLH is a rectangle, because it has 4 angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ECLH, side CL must be equal to the opposite side EH. But CL in total it is 8 plus 8 is 16, therefore the opposite side EH must be also equal to 16 units in its length. In the next step, we extended the radius BQ of this medium circle by straight line until it touches the circle at point S. By doing this construction, we created 2 smaller quadrilaterals, the small quadrilateral ESBH, and the small quadrilateral ESBH. We have 1, 2, 3 right angles, and therefore this fourth angle must be equal to 90 degrees in its size. Likewise, we created quadrangle SCLB. In the quadrangle SBLB we have 1, 2 3 degrees, and therefore this 4 pieces must be equal to 90 degrees in its size. Therefore, quadrangle SCLB is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle SCLB, side SB must be equal to the opposite side CL. But CL is 16, therefore SB must be also equal to 16 units in its length. SB equals to 16. So in the next step we did another construction, that is to say, from point P we draw perpendicular on SB. Again, from point P we draw perpendicular on SB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and SB. This point is point X. When doing this construction, we get the small quadrangle ASXP. Inside the small quadrangle ASXP, we have 1, 2, 3 degrees. Again, 1, 2, 3 degrees, and therefore this function, this angle must be also equal to 90 degrees in its size. Therefore, quadrangle ASXP is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle APXS, side AP must be equal to the opposite side SX. But AP is 5, therefore the opposite side SX must be also equal to 5 units in its length. What is the length of this missing line segment XQ? XQ equals to SB, that is 16, minus SX, that is 5, minus QB, that is 6. 16 minus 5 minus 6 is 5, so XQ equals to 5. In the next step, I call it the right green triangle PXQ. Before that, we join points P and Q together by straight line. We have an external line between those two circles. It's point J. Whenever we have an external line between two circles, we can implement rule 10. According to rule 10, the third line that connects the centers of those two circles together, that is the third line PQ, must pass for their touching point, that is point J. Or PJQ is one third line according to rule 10. If PJQ is one third line, it means that PQ must be also in total equals to PJ plus JQ. So PQ equals to PJ, that is 5, plus JQ, that is 6. In total, PQ must be equal to 11 units in its length according to rule 10. In the next step, we copy the right triangle PXJ in a new page and we implemented the Pythagoras theorem on this right green triangle PXJ. This is the right triangle PXJ. This is a copy from the drawing. According to the Pythagoras theorem, PQ square, that is the square of the opponent, equals to PX square plus XQ square. PQ is 11, therefore PQ square is 11 square, that is 121, and it is equals to PX square. PX is the resistance side, so it is PX square plus XQ square. XQ is 5, therefore XQ square is 5 square, that is 25. Here we subtracted 25 from this equation, and finally found out that 121 minus 25 is 96, so 96 equals to PX square. We substituted 96 by 16 times 6. So we found out that Px squared equals to 16 times 6. Here we took out all of the equation and found out that Px equals to the square root of 16 is 4. So inside the root we have to leave 6. So Px equals to 4 times square root of 6 units in its length. This is side Px is equal to 4 times square root of 6 units in its length. We only found out that ASXP is a rectangle and the opposite sides of a rectangle are equal to each other. So in rectangle ASXP, side Px must be equal to the opposite side AS. But Px is 4 times square root of 6, therefore the opposite side AS must be also equal to 4 times square root of 6 units in its length. In the next step we join points Q and S together by straight line. Q is the center of this medium circle, S is the center of this big circle, so QS is the straight line that connects their centers together. We have an external line between the medium circle and the big circle at point Y, therefore we can implement rule 10 here. According to rule 10, the straight line that connects the centers together, that is the straight line QS, must pass through point Y, that is the attaching point. For QYS is one straight line. If QYS is one straight line, it means that QS must be equal to QY, that is 6, plus YS, that is 8. So in total, QS must be equal to 6 plus 8, that is 16. QS equals to 6, QS in total equals to 6 plus 8, that is 14. So in the next step we did a construction, that is to say from point Q we do perpendicular on CL. Again from point Q we do perpendicular on CL. So this angle comes to 90 degrees and this angle also comes to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and CL. This point is point T. By doing this construction we can do the quadrilateral QT and B. Inside quadrilateral QT and T we have 1, 2, 3 rectangles, and therefore this fourth rectangle must be equal to 90 degrees in size. Therefore quadrilateral QTLB is a rectangle, but we also know that the opposite sides of a rectangle are equal to each other. So rectangle QTLB side QB must be equal to the opposite side TL, but QB6, therefore the opposite side TL must be also equal to 6 units in its length. What is the length of this missing line segment ST? ST is equal to SL minus TL. So ST equals to SL, that is 8, minus AL, that is 6. So ST in total equals to 8 minus 6, that is 2. So in the next step I copy the right green triangle QST in a new page and implement the Pythagoras one on this right triangle QST. So actually this is the right triangle QS. Actually we implemented the Pythagoras one on the right triangle QSK. This letter is K, not T but K. We implemented the Pythagoras one on the right triangle QSK. This letter is K. So this is the right triangle QSK, that is the complete from the drawing. And this right triangle QSK, SQ squared, that is the square of the hypotenuse, equals to SK squared plus KQ squared. QS is 14, therefore Q squared is 14 squared, that is 196, and it is equal to SK squared. SK is 2, therefore SK squared is 2 squared, that is 4, plus QK squared. QK is the missing side, so electricity. So in total, if you found out that 196 equals to 4 plus QK squared. If subtracted 4 from this equation, if we found out that 196 minus 4 is 192 equals to QK squared. We substituted 192 by 64 times 3, and 64 times 3 equals to QK squared. Here to hold out the equation, if I found out that QK equals to the square root of 64 is 8, so inside the root we left only with 3. So in total we actually found out that QK equals to 8 times square root of 3 units in its length. This is the missing line segment QK, that is equals to 8 times square root of 3 units in its length. This is quadrilateral SCKQ. In quadrilateral SCKQ we have 1, 2, 3 right angles. Therefore, this form missing angle must be also 190 degrees in size. Therefore, quadrilateral SCKQ is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. So, a rectangle SCKQ, side KQ must be equal to the opposite side SC. But KQ is 8 times square root of 3, therefore, the opposite side SC must be also equal to 8 times square root of 3 units in its length. Our task is to find out the area of this big rectangle EFQH. The area of an rectangle equals to the width of the rectangle times the length. The width of a rectangle EFQH is AH and the length is AF. Then again, the width is EH and the length is EF. EH equals the width EH equals to 16, and the length EF equals to EA plus AS plus SC plus CF. Again, the length EF equals to EA plus AS plus SC plus CF. So the rectangle rectangle EFQH equals to 16 times EA. EA is 5 plus AS. AS is 4 times square root of 6. SC is 8 times square root of 3 plus CF is 8. So in total 16 times 5 plus 4 times square root of 6 plus 8 times square root of 3 plus 8 is the area of rectangle EFQH. The value of this expression in total is equal to 586.47 square units in its size. So if you found out that the area of this rectangle EFQH is equal to 586.47 square units in its size. So we finish with the first question. In the next step I presented you the second question, and we solve the second question by using two different methods. Our task in the second question is to find out the area of this circle. So in the drawing we have a circle. This is called AB, this is equals to 8 units in its length. This is called PQ, this is equals to 6 units in its length. This is angle PMQ, this is the right angle. Again, our task is to find out the area of this circle. So first of all, I presented to you rule 29 and we implemented rule 29 in our drawing. According to rule 29, paper angles that subtend on the same arc are equal to each other. In the drawing we have a circle. This is paper angle BDC that subtend on arc BC. Likewise, we have another paper angle BEC that subtend on the same arc BC. And because of the fact that those two paper angles subtend on the same arc, they must be equal to each other in their sizes. That is to say, alpha equals to beta. So I can implement rule 29 in our drawing. Because in our drawing, if we focus on arc BQ, this is set angle BAQ that subtend on arc BQ. Likewise, we have this is set angle BPQ that is also subtend on the same arc BQ, and because of the fact that those two paper angles subtend on the same arc BQ, they must be equal to each other in their sizes. So if the size of this paper angle BAQ is alpha, then the size of this paper angle BPQ must be also equal to alpha. Likewise, we focus on this arc AP. This is paper angle PQA that subtend on arc AP. Likewise, we have another paper angle PB8 that subtend on the same arc AP. And because of the fact that those two paper angles subtend on the same arc AP, they must be equal to each other in their sizes. So if the size of this angle is beta, then the size of this angle must be also equal to beta, according to rule 29, because they subtend on the same arc AP. In the next step, we presented you rule 13 and implemented rule 13 in our drawing. According to rule 13, a central angle is twice as large as the paper angle subtended on the same chord or the same arc. In the drawing we have a circle. This is paper angle ACB that subtend on arc AB. Likewise, we have central angle AOB that subtend on the same arc AB. And according to this rule 13, the size of the central angle AOB is twice as big as the size of this paper angle ACB that subtend on the same arc. And the size of this paper angle ACB is theta, and therefore the size of central angle AOB that subtend on the same arc AB must be equal to 2 theta. So we can implement rule 13 in our drawing. Right in our drawing, we draw the central angle AOP that subtend on arc AP. Likewise, we have also paper angle EQB that is also subtend on arc AP. And according to rule 13, the size of central angle AOP is twice as big as the size of this paper angle that subtend on the same arc AP. But the size of this paper angle AQP is better, therefore the size of this central angle AOP must be equal to 2 beta. Likewise, according to rule 13, of course. we focus on this arc BQ. I draw the center angle BOQ that subtend on arc BQ. But we also have peripheral angle BAQ that subtend on the same arc BQ. And because of the fact that the size of peripheral angle BAQ is alpha, the size of center angle BOQ must be equal to 2 alpha, because they both subtend on the same arc BQ. In the next step, we define angle AOB is y and this angle POQ is x. And we have the rule that the sum of the angles around any point is equal to 360 degrees. So the sum of the angles around point O must be equal to 360 degrees. So which angles we have around point O, that is the center of the circle, we have 2 alpha plus 2 beta plus x plus y equals to 360 degrees. Until the end, around point O, the sum of the angles must be equal to 360 degrees. That is to say, 2 alpha plus 2 beta plus x plus y equals to 360 degrees. But we already found out that 2 alpha plus 2 beta equals to 180 degrees. So we can substitute 2 alpha plus 2 beta by 180 degrees. So we have 180 degrees plus x plus y equals to 360 degrees. Here we subtract 180 degrees from this equation, and we found out that x plus y equals to 360 degrees minus 180 degrees is 180 degrees. So x plus y equals to 180 degrees. In the next step, I presented to you rule 30 and implemented rule 30 in our drawing. According to rule 30, center angles that subtend on equal chords are equal to each other. In the drawing second, this is center angle COD that subtend on chord CD. Likewise, there have another center angle AOB that subtend on chord AB. If chord AB equals to chord CD, that is to say those two center angles subtend on equal chords, then they must be equal to each other in their sizes. That is to say alpha equals to beta. So according to rule 30, if 2 or more center angles subtend on equal chords, they must be equal to each other in their sizes. So we can implement rule 30 in our drawing. So first of all, I copied this circle to a new page, and then I copied also center angle AOB that is equals to y divided in size, and chord AB that is equals to 8 units in its length. So this is the circle that I copied from the original drawing. This is the center angle AOB that is equals to y divided in size, and this is chord AB that is equal to 8 units in its length. In the next step, we did the construction, that is to say, from point B, we do chord BC that is equal to 6 units in its length according to our construction. Again, from point B, we do chord BC in such a way that it will be equal to 6 units in its length. So BC equals to 6, chord BC equals to 6 according to our construction. In the next step, we join points on C together by straight line. By doing this construction, we get the center angle BOC that subtend on chord BC that is equal to 6 units in its length. So if we have center angle BOC that subtend on a chord that is equal to 6 units in its length. Likewise, in the original drawing, we have center angle POQ that is also subtend on chord that is equal to 6 units in its length. And because of the fact that those two center angles, they both subtend on equal chords that is equal to 6 units in its length, they must be equal to each other in their sizes. But the size of this center angle POQ is x, therefore the size of this center angle POQ must be also equal to x according to rule 30. According to rule 30, center angles that subtend on equal chords must be equal to each other in their sizes. Those two center angles subtend on equal chords that is equal to 6 units in its length, and therefore they must be equal to each other in their sizes. But the size of this center angle POQ is x, therefore the size of this center angle BOC must be equal to x degrees in its size according to rule 30. Okay, so by doing this construction, we get that the big angle AOC, the big angle AOC equals to x plus y degrees in its size. Again, the big angle AOC equals to x plus y degrees in its size. But we already found out that x plus y equals to 180 degrees. That is to say, the big angle AOC equals to 180 degrees in its size. And we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore, AC is a straight line. But AC is a straight line that touches the circle at 2 points, A and C. Therefore, AC is a chord. AC is a chord that passes through point O, that is the center of the circle. And we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, AC is the diameter of the circle. So here we can implement rule 7. According to rule 7, if a peripheral angle subset on the diameter of the circle, that is equal to 90 degrees in its size. In the drawing we have a circle. This is peripheral angle ACB that subset on the diameter of the circle, that is 4 AB. And therefore, peripheral angle ACB must be equal to 90 degrees in its size. We can definitely implement rule 7 in our drawing, because in our drawing we have peripheral angle ABC that subset on the diameter of the circle. Peripheral angle ABC subset on chord AC, that is the diameter of the circle. Therefore, according to rule 7, it must be equal to 90 degrees in its size. In the next step, I copied the right triangle ABC in the new page and we implemented the paradox on this right triangle ABC. So, okay, this is the right triangle ABC, this is a copy from the original drawing. Side AB equals to 8 units in itself, side BC equals to 6 units in itself according to our construction. AC is the opponent AC is also the diameter of the circle. If the radius is out, then the diameter must be equal to 2r. This angle equals to 90 degrees according to rule 7. So in the right triangle ABC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is 2r, therefore AC squared is 2r squared, that is 4r squared, and it is equals to AB squared. AB is 8, therefore AB squared is 8 squared, that is 64, plus BC squared. BC is 6, therefore BC squared is 6 squared, that is 36. So in total 4r squared equals to 64 plus 36. 64 plus 36 is 100. So 4r squared equals to 100. Here we divided this equation by 4, and we found out that r squared equals to 100 over 4 is 25. So r squared equals to 25. Here we took a root out of this equation, and we found out that the radius r equals to the square root of 25, that is 5. So if we found out that the radius r of this circle equals to 5 units in its length. Our test is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared. So it is pi r. The area of our circle must be equal to pi r squared. But r is 5, therefore r squared is 5 squared, that is 25. So in total, if you found out the area of our circle, it is equal to either 25 pi square units in size, or in terms of numbers, it is equal to 78.54 square units in its size. We finish with the first question. We finish with the first method of the second question. In the next step, I explain to you how to find out the area of this circle according to the second method. In the second method, we use some of the fields that we already found out in the first method. In the first method, we have already found out that those two angles are both equal to alpha, and those two angles are both right angles. So use it in the second method. This is the right triangle A and B. In the right triangle A and B, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the right triangle P and Q, this angle equals to alpha. this angle equals to 90 degrees, and therefore this third BC angle must be equal to 90 degrees one solve according to the sum rule that the sum of the angles in any triangle is equal to 180 degrees. Those two triangles are similar to each other according to angle similarity rule. That is to say, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees one alpha, therefore they are equal to each other. So I shall find out that all the figures of the big right triangle A and B correspond equal to all the figures of this right small triangle PMQ, and therefore those two right triangles are similar to each other according to angle similarity rule. So if we found out that the right triangle A and B is similar, this is the sum similar to the right triangle PMQ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AB of the right triangle A and B over side PQ of the right triangle PMQ is equal to side AM of the right triangle A and B over side PM of the right triangle AMQ, and it is also equal to side VM of the right triangle A and B over side MQ of the right triangle PMQ. Again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between the sides. So we derive that side AB of the right triangle A and B over side PQ of the right triangle PMQ is equal to side AM of the right triangle A and B over side PM of the right triangle PMQ, and it is also equals to side VM of the right triangle AMB or side MQ of the right triangle PMQ. AB is 8, PQ is 6, so it is equals to AM over PM. Here we divided both the numerator and the denominator of this number by 2 and found out of it that 8 over 2 is 4 and 6 over 2 is 3. So in total we found out that 4/3 equals to AM over PM. We multiplied both the numerator and the denominator of this number by A. We found out that 4A over 3 equals to AM over PM. A over A is 1, so it is allowable to multiply anything by 1. We will not change the value of the expression by multiplying it by 1. What is the meaning of this equation? The meaning of this equation is that if AM equals to 4A, then PM must be equal to 3A. Again, if AM equals to 4A, then PM equals to 3A. And again, we should find out that if AM equals to 4A, then PM must be equal to 3A. Likewise, those two sides of the equation are also equal to each other. PB over PQ is 4/1, and it is equals to BM over MQ. So 4/1 equals to BM over MQ. 4/1 equals to BM over MQ. We multiply both the numerator and the denominator of this number by B. And we found out that 4B over 3B equals to BM over MQ. What is the meaning of this equation? The meaning of this equation is that if BM equals to 4B, then MQ must be equal to 3B. And again, if we found out that if BM equals to 4B, then MQ must be equal to 3B. PB is a chord in this circle. PB is a chord, it is absolutely a straight line. So if we focus on the right side of the straight line PB at point M, here the sum of the angles must be equal to 180 degrees according to Rule 3. Rule 3 says that the sum of the angles from one side of the straight line is equal to 180 degrees. So each angle we have at the right side of the straight line PB at point M, we have this angle that is the right angle, plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to Rule 3. Therefore this missing angle must be equal to 90 degrees in its sides. In the next step we join points B and Q together by straight line. By joining points B and Q, we render the right triangle MBQ. So copy the right triangle MBQ in a new page and implement it on this right triangle MBQ, the Pythagoras theorem. So this is the right triangle BMQ that I got from the original drawing. This right triangle BMQ, BQ squared, that is the square of the hypotenuse, equals to MB squared plus MQ squared. BQ is the missing side, so we need to see this. So it is BQ squared equals to MB squared. MB is 4B, therefore MB squared is 4B squared. 4B squared is 16B squared. Plus MQ squared. MQ is 3B, therefore MQ squared is 3B squared. 3B squared is 9B squared. 16b squared plus 9b squared is 25b squared. So in total we should find out that bq squared equals to 25b squared. If we took out of this equation, we find out that bq equals to the square root of 25 is 5 and the square root of b squared is b. So in total bq equals to 5b units in its length. This is side bq that is equals to 5b units in its length. In the next step, we calculated the area of this triangle ABQ, and we created an equation that said the area of triangle ABQ according to the first method must be equal to the area of triangle ABQ according to the second method. In the first method, we calculated the area of this triangle ABQ according to the formula that says that the area of any triangle equals to the base of the triangle times the height to the base over 2. We choose the base as AQ, so the area of triangle ABQ equals to the base AQ times the height to the base, that is MB over 2. So according to the first method, the area of this triangle ABQ equals to the base AQ times the height to the base, that is MB over 2. And it must be equal to the area of this triangle ABQ according to the second method. In the second method, we found out that actually we have a triangle ABC that could be any triangle. This triangle ABC, side AB equals to A units in its length, side AC equals to B units in its length, side BC equals to C units in its length. This is angle theta, angle BAC equals to theta. So in this triangle ABC, the area of this triangle ABC that could be any triangle equals to A times B times sinus theta over 2. So the area of this triangle ABC equals to the multiplication of two sides by each other times the angle between those two sides divided by 2. So the area of this triangle AB and C equals to A times B times sinus theta over 2. Use the new formula in order to find out the area of this triangle ABQ. According to the new formula, the area of triangle ABQ equals to AB times BQ times sinus the angle between the two sides AB and BQ. This is angle ABQ divided by 2. So in total, the area of this triangle ABQ according to the second method, it is AB times BQ times sinus angle ABQ over 2. According to the second method, the area of this triangle ABQ equals to AB times BQ times sinus the angle between side AB and BQ, that is angle ABQ divided by 2. So according to this equation, the area of triangle ABQ according to the first method must be equal to the area of triangle ABQ according to the second method. Here we have 2 on both sides of the equation, so 2 will get cancelled. We have to find out the value of sinus angle ABQ. In order to find out the value of sinus angle ABQ, we implemented the law of sines in our drawing. What is the law of sines? First of all, the law of sines is true in any triangle. This is triangle ABC that could be any triangle. Side AB equals to C units in its length, side AC equals to B units in its length, side BC equals to A units in its length. This is angle alpha, this is angle beta, and this is angle gamma. This triangle ABC that could be any triangle, according to the law of sines, the following equation is 2. That A over sinus alpha equals to B over sinus beta equals to C over sinus gamma equals to 2R. And 2R is the diameter of the circle that blocks the triangle ABC. Repeat again, 2R is the diameter of the circle that blocks this triangle ABC. So we can implement the law of sines in our drawing. In our drawing, we have triangle ABQ. So triangle ABC could be any triangle, therefore we can implement it on any triangle. And this is the circle that blocks triangle ABQ, and therefore 2R is the diameter of the circle. According to the law of sines, if we implement the law of sines in triangle ABQ, the following equation will be 2 AQ or sinus angle ABQ equals to 2R. And 2R is the diameter of the circle that blocks this triangle, triangle ABQ. And repeat again, according to the law of sines, if you implement the law of sines in triangle ABQ, the following equation will be true that AQ or sinus angle ABQ equals to 2R. Again, according to the law of sines, the following equation will be true that AQ or sinus angle ABQ equals to 2R. This equation is the implementation of the law of sines in triangle ABQ. Here we multiply this equation by sinus angle ABQ and we divide it simultaneously by 2R. And finally found out that sinus angle ABQ equals to AQ over 2R. Now we can substitute sinus angle ABQ by AQ over 2R. Here. We substitute sinus angle ABQ by AQ over 2R. So we did it, and we found out that AM times BM equals to AB times BQ, and sinus angle ABQ equals to AQ over 2R. We have AQ on both sides of the equation, so AQ will get cancelled. After cancelled AQ, we left in this side of the equation only with MB, that is equals to AB times BQ over 2R. Here we multiplied this equation by R, and we divided by MB simultaneously, and found out actually that the radius R of this circle is equal to AB times BQ over 2 times MB. AB is 8 times BQ. BQ is 5B over 2 times MB. MB is 4B. So in total, we found out that R equals to 8 times 5B over 2 times 4B. We have B in the numerator and B in the denominator, so B will get cancelled. We have 8 in the numerator and 2 times 4, that is 8 in the denominator. So those numbers also get cancelled, and we left only with 5. So we found out that the radius R of this circle equals to 5 units in its length. Our test is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. Therefore, the area of our circle must be equal to pi times the radius of our circle squared. But the radius of our circle squared is r squared. Therefore, the area of our circle must be equal to pi r squared. But r is 5, therefore r squared is 5 squared, that is 25. So in both methods, we found out that the area of this circle equals to either 25 pi square units in size, or in terms of numbers, the area of this circle equals to 78.54 square units in its size. Okay, thank you very much.